So we're going to continue this containers method, starting with this graph container. Last week we introduced this classical Kleitman-Winston graph container theorem. It's this one I copy here. Let's go through what it's talking about. We have a graph, and we have some parameters. And oftentimes we can use this inequality, so it's enough to verify this inequality. We have some parameters satisfying some inequalities. As long as the graph is locally dense, some sort of supersaturation phenomenon, you can also think of this as supersaturation in terms of edges. Locally over some not too small sets of vertices. Then the theorem says there exists a collection of subset of vertices which can serve as a container for independent sets. What does it mean? Well, every independent set is contained in the graph, is contained in one of these containers, Ci. And this is the first property which justifies the name of container. It contains all the independent sets. Second thing is that each container is not too big. For otherwise, I can just take a single container, which is the set of all vertices. You can take a single container. Every independent set is in there. But this container is pretty much useless. It's too large. And the point is that we have some parameter which is reasonably small, as long as you have reasonably strong locally denseness condition. And the consequence of this container is that, well, in the proof, we've seen how here's roughly the proof, a sketch. I think it's worth to go through this picture again. We give a max degree ordering of the vertices, and basically how we do is we analyze how an independent set can be distributed over the vertices. Our goal is using locally denseness to be able to identify an independent set through a very small fingerprint. So we go through the max degree ordering, and we pick out the vertices that are in this independent set I. If it's in there, of course, we pick out all its neighbors because we are picking independent sets. Then we reorder the vertices in max degree ordering, and we start again. We every time pick out the next vertex in I and kick out its neighbors. By doing so, we can quickly shrink the remaining sets A, where, by definition, the selected set S, which is the fingerprint, is a subset of I. And since all the vertices we kick out are those that are not eligible to be in I, the remaining of the independent set I must lie in this remaining set A. So the fingerprint plus the remaining set, as long as it's not too small, will together serve as container for this independent set. The fingerprint is used to group them together. The key thing is that even though in this algorithm we fix I, but if now we give an S, the fingerprint, we know how this ordering looks like. We can completely recover this process without knowing I. In other words, A depends solely on S, not on I. So it could be that two different independent sets, I and I prime, produce the same fingerprint. So this fingerprint is to create this clustering phenomenon to group the independent sets into a few groups. And these few groups are these containers Ci. Okay. The consequence of this container is that how can we then count independent sets of size M? Well, we first choose fingerprint of size Q, which we just use the crude bound and choose Q. And then after choose Q, we know that there are n minus Q vertices left in the independent set I, which lies in this remaining set of size R. And if you recall the proof, this locally denseness is used so that every time, whenever the remaining set is bigger than R, we know that it's locally dense, meaning that the next vertex that we picked out has high degree will kick out at least this beta proportion of the remaining set. So every time we shrink by a factor of 1 minus Q. Okay, to get the last time, where did we stop? Did we finish the, okay. So last time in the proof, we introduced this algorithm in details. And we finished the proof using the claim that the final set A is not large. Okay, given that final set is not large, we finished the proof. So this time, let's prove this claim that the final set A cannot be larger than R. Any questions so far? Okay. Okay, so if there's no question, let's finish this proof here. Let's try to prove this claim. The proof is basically what I just said. Let me mention one more consequence of this is that we can also count the total number of independent sets. So another consequence is that the total number independent sets of all sizes in the graph G is at most what? And choose Q. We're going to first choose the signature because the number since signature determines A, which in turns determines the container C. So the number of signatures equals to the number of containers is upper bound. This number of fingerprint or signature, doesn't matter, fingerprint upper bounds the number of containers. And then, since we know each container has size at most capital R plus Q, each such container contains at most 2 to the its size number of independent sets. So we just simply multiply by 2 to the R plus Q. So this crude bound sometimes is also useful. We will see later in the application. Okay. All right, so let's now prove this claim. The proof is basically, as I said, without the writing down the calculation, every time, because of the max degree, the next vertex we kick out is of maximum degree. And since the density is beta, every time we kick out beta fraction. So the number of vertices available in set A is shrink by a factor of 1 minus beta. Carrying out Q times, it must be less than R because of the hypothesis. Okay. Let's prove it. We need to prove, we are left to prove the final set A is not too large. Okay, let's start with a new page. So as I said, it follows from locally denseness. Okay. So now in this process, at every step, at the I step, we have the current A. So let's say at the beginning of the I step, let AI be the current set of remaining vertices at the beginning of step I. Let's analyze each step. Let AI, for every I in Q, let AI be the set of active vertices, be the active set. Prior to the ith iteration. So what does it mean? A1, this is the set prior to the first iteration. And remember, we set the initial A. This is the initial A. Is V of G. And AQ plus 1 is, we only carry out Q steps. So AQ is the active set just prior to the Q's iteration, the last step. So AQ plus 1 is the final A. Okay. Now, suppose to the contrary that A is larger than R. Suppose A is at least R. Let's try to derive a contradiction. Now, we know that at the I step, we select. So this is AI, and we order it by max degree ordering, right? And we know at this step, we choose the vertex VTI according to our algorithm. This is the first vertex along the max degree ordering of AI that lies in I. We choose this one. So we need to delete all these guys. So let's give it the name. Let's call it, suppose this is, let me call, this is yeah, that's fine. So every time I rename V1, V2 according to the max ordering of the current set AI. So we're going to delete all the previous ones. Let A prime to be A I minus V1 VTI minus 1. Right up to where you delete the first vertex in I, let's call it, remove this, call this A prime here. Okay. Now, first of all, A prime is still, since I is at most Q, A prime is still at least as large as the final set A. we have A prime is at least final set A, which is at least R. Then by locally denseness, we have the number of edges induced by A prime is at least beta fraction of A prime choose 2. So that, and this vertex is the maximum degree by the ordering among A prime, the subgraph induced on A prime. So this implies that the degree in A prime, in G A prime of the vertex VTI is at least the average degree of A prime, which is this number, okay, equals to beta times A prime minus 1. This is just calculation, no problem. That means we have lots of neighbors. Beta fraction, sort of beta fraction. And these ones, we're going to kick them out to move to the next AI, the AI plus 1. So, so what that means thus, in step 2, when updating the set A, we delete at least how many vertices? Well, we first delete all these vertices right before this first vertex in I. We also remove, we put this guy in S. So this is also removed. So we remove TI vertices here, at least TI vertices, plus the neighborhood of the TI's vertex, which is at least this much, beta A prime minus 1. What is A prime minus 1? A prime has size AI minus TI plus 1. So this equals to minus this many vertices. That's A prime, right? Minus 1. Okay. And if you do this calculation, I will skip the calculation, is at least beta fraction of AI. And this is the process of passing from AI to AI plus 1. Okay. So AI, from AI to AI plus 1, we delete beta fraction of the AI. This implies AI to AI plus 1 shrink 1 minus beta factor, which then implies the final A is at most, we carry out Q steps. We start from the whole set of vertices. So altogether, this is less than R that we know by hypothesis. Okay. Maybe I should put less equal. So this is strict. Okay. This is a contradiction because we assume A is strictly larger than R. But we know that it cannot be. Basically, nice, simple but nice proof. Okay. Any question about the details? No? Okay, good. So let's move on. We're going to see some applications. The first application is, as I said, counting problems. So the first counting problem we're going to look at, we've mentioned the counting problems. For example, we can count how many triangle free graphs there are, and any extremal problem you can ask for a counting problem. And we can also ask, for example, EKR is the extremal results. Largest k-uniform intersecting family has size n-1 choose k-1. Then we can also ask how many k-uniform intersecting families there are. Since, as I said, every sub-hypergraph of intersecting hypergraph is also intersecting trivially. So we have at least, in the labeled sense, at least 2 to the n-1 choose k-1 by taking all possible sub-hypergraph of this guy. We get a lower bound of this number, 2 to the maximum size, the extremal size. We're gonna see the first application is to prove matching upper bound at least asymptotically in the logarithm up here, tight upper bound. Okay. And since we are talking about graph containers for independent sets, we're going to phrase these counting intersecting families in terms of counting independent sets. This is through using Knaser graphs. So we've mentioned in last semester, but if you don't remember, that's fine. I'm going to remind you how to phrase Erdős-Corrado in terms of the statement about independent sets in Knaser graphs. Okay. So here's the theorem. Maybe let me first write counting intersecting family. So here's the theorem. For any k at least 3, n at least 2k plus 1, then the number of intersecting families or hypergraphs is equals to 2 to the 1 plus little o1 n-1 choose k-1. As I've just mentioned, this is the trivial lower bound by taking all possible sub-hypergraphs of the intersecting hypergraph. It's tied up to this 1 plus little 1. Now, if you're careful, you might notice that our bound for n starts from 2k plus 1. Whereas in Erdős-Corrado, we start from n at least 2k. It's true already for n at least 2k. So there is a reason here we cannot hope to have n at least 2k as in Erdős-Corrado. So this bound on n is also optimal. This is a result of use of Balog-Chagny-Das, Michel Delcourt, myself, and Marian Charizade about 10 years ago in 2014. So here's a remark. In Erdős-Corrado is true for all n at least 2k. Here, n at least 2k plus 1 is optimal. We cannot improve it. This is because when n equals 2, let's look at this boundary case, the number of intersecting family is exponentially larger than this. They're a lot more than this many. Why? When n equals to 2k, apart from this trivial family, intersecting family that all share a common element, there's another extremal family. This is of size n minus 1 choose k minus 1, right? There's another family that looks like this. You have you have n is the ground set. You can always cut it into half sets of size k here, n equals to 2k, right? So by cutting it into half this way, this way, this way, this way, we can partition into two complementary set of size k. Now, another extremal family, not like this one, is for every possible such cut pairing, you choose exactly one of them. Exactly one. Because this k set is only disjoint from this k set when you ground sets 2k. It intersects all other k sets. So choose exactly one from each halving of n. Now you have this A bar, this pairing, right? For each um, for each such pair of complementary pair, we have three choices to build intersecting family. We either choose nothing, we don't choose any one of them, or we choose one of them, or we choose the other one. You have three choices for every such pair. Three choices. How many number of pairs? Well, n choose k, which is n choose n over 2, right? But I think you need to divide it by 2, because n choose k, this k and n choose this k result in the same pair. So divide it by 2. Okay. Equals to 1/2 n choose n over 2. If you do the calculation, this is the same as n minus k minus 1. So this is why this case is special. Now, for all this many number of pairs of k sets and its complement, you have three choices. So the number is at least 3 to the n minus 1 choose k minus 1, which is exponentially larger than the above. So this is optimal. Now let's see how we prove this. The binary machinery, it's fairly simple to prove this. The proof can be summarized in 2 sentences. Well, we want to use container, so we're going to phrase counting intersecting families in terms of counting independent sets in Knaser graph, and use Kleiman-Winston graph container theorem. That's the first sentence. Now, to use that, we need to prove some locally denseness property of the Knaser graph. Here comes the second ingredient. We use the spectral method. In particular, we use the spectrum gap for Knaser graph, and then we can invoke expander mixing lemma to prove that we have locally denseness supersaturation. And putting things together, you do some calculation, boom, we have this result. Okay. So let's write down the idea. We're going to count independent sets in Knaser graph using Kleitman-Winston graph container. For local to verify and use spectral method. In particular, expander mixing lemma. To verify the locally denseness condition. Okay, so let's first translate the problem into counting independent sets in Knaser graph. I will go through this part relatively fast because we've mentioned this before. But if the first time seeing it, this shouldn't be too hard to follow. So the definition, we have, what's a Knaser graph? The Knaser graph Knaser graph, Kn, let's say n k. It has vertex set v and e, right? With two parameters, little n and little k. So how do we use these two parameters? The vertex set of the Knaser graph are all the size k subset of little n. And for the edge sets, we have two sets, two vertices, which are k sets in n. They are adjacent in the Knaser graph, if and only if they are disjoint. Okay. So I think yeah, okay. Now, good. So if we have a k-uniform family that's intersecting, this is a family consisting of k sets on some ground set of size n, which is basically a set of vertices, right? This family, you can view it as a set of vertices of the Knaser graph. Now, what's the special about this set of vertices? We know they are intersecting, so they don't satisfy that pairwise they are not disjoint, meaning that pairwise there's no edge between them. So every k-uniform intersecting family corresponds to exactly one of the independent sets in Knaser graph. So there's a one-to-one correspondence, one-to-one correspondence of intersecting family and independent sets in Knaser graph. Okay, now we need to verify the good, we know. So counting independent sets becomes, sorry, counting intersecting families becomes counting independent sets in Knaser graph. We need to verify the locally denseness. So now think of this G as our Knaser graph. We need to verify, we have to choose some RQ beta so that this is true. And then we have to verify that for this beta that we chose, the Knaser graph is locally dense. Then we will get these containers. This is where the spectral method kicks in using expander mixing. We will use the following version by Alon and Chen. It says the following. We have a graph G. Think of this as the Canesian graph. You have n vertices. This graph is regular. So every vertex has degree capital D, D regular, with minimal eigenvalue. So by eigenvalue, I mean you look at the adjacency matrix of G. This is n by n matrix where the ij's entry is 0, 1 matrix, where the ij's entry is 1 if vi and vj form an edge, 0 otherwise. For this matrix, if the minimal eigenvalue is lambda, then for any set of vertices in our graph, we have the following pseudo-randomness property. The number of edges in G induced by the set S is at least capital D over n S squared over 2. Okay? Plus lambda over 2n times S n minus S. So let me give some comments about this bound. It looks a little bit complicated, the formula, but all we need to care about is this term. This term I claim that when lambda is small, it's an error term. So this is the main term. Why this is the main term? If the graph is random, so here's the remark. If G is random, this term is basically the number of edges you expect to see. In expectation, how many edges we expect to see? Where on the set S, we have this many pairs total. For each such pair, the probability, look, this is our graph, n vertices, every vertex has degree D. So if the graph is completely random, a pair of vertices are adjacent with probability D over n, right? So for all such pairs, each pair of this probability forming an edge, this is what you expect it to see, which is roughly this guy. Now, when lambda is small, compared to D, which is when G is pseudo-random. This is exactly when G is pseudo-random. Okay, now what do we have? You have D over n here, you have lambda over n. These are more or less the same. Forget about it, order of magnitude. So this is a lower order term of this. This is an error term. Okay. Any questions about the statement? The expanded mixing is even stronger. We have both lower bound and upper bounds. For now, it's enough to use this version where we have this lower bound. Okay. Now we have this. We also need to know the spectral information about the Canesian graph in order to use this expander mixing. This is already done by Lovatz in the late 70s. So Lovatz, 1979, proved that for Canesa graph, the minimum eigenvalue of the Canesa graph is lambda equals to negative m minus k minus 1, k minus 1. Okay, you can rewrite this as negative k over m minus k times the degree d. What's the degree d for Canesa graph? Well, d, you are adjacent to Canesa graph is symmetric. Vertex is adjacent to all the vertices that are disjoint from it. You have m minus k other vertices, elements out of the set corresponding to this vertex, and you have to choose k of them to form a vertex in the Canesa graph. This is your degree. Number of vertices in the Canesa graph is n choose k, obviously. Okay. Now we get combining these two, we can get the supersaturation. The supersaturation goes as follows. For locally denseness, whichever way you want to call it, is for any epsilon and any set S of size slightly above m minus 1, choose k minus 1, where S is a subset of vertices of the Canesa graph. Then we have this set in the Canesa graph is dense, locally dense. This is at least epsilon over 1 plus epsilon times dn over capital N m minus k times S choose 2. So this guy will be our beta. Oh, too light. So beta fraction of the edges are there. You can think of these are roughly constant. This is also not too small, so roughly epsilon fraction when k is linear in n. This is constant, so roughly epsilon fraction of edges adjacent. Okay, now the proof of this, I will leave it for you to verify. Exercise. Okay, you basically use expander mixing lemma. Use the previous two. Use a long chain. Tron. The bound here on S is necessary. This is optimal, remark. This is almost trivial remark on S, optimal, because what's the independence number of Canesa graph? The largest independence sets, remember, it corresponds to the largest intersecting family, which by EKR is m minus 1, choose k minus 1. Okay, so if you drop below this value, there could be no edge at all. But once you're above the independence number by a positive fraction, you suddenly see a positive fraction of edges. This is a supersaturation. Okay. Any question? All right. Now let's we have the locally denseness verified. Let's apply Kleiman-Winston using this locally denseness that we just proved to get a collection of containers for independent sets in Canesa graph. In other words, we get a set of containers for k-uniform intersecting families on ground set N. Now we can use, right? Now use Kleiman-Winston container to get containers for intersecting families. Proposition. Here's the how we choose the parameter capital R, little q, beta, blah, 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 for epsilon bigger than 0, k at least 2, n at least 2k plus 1. We're going to choose R, the supersaturation threshold. R is the threshold above which we have the locally denseness. So here we have the locally denseness. We're going to just set R to be slightly above the independence number, to be this number. Is 1 plus epsilon n minus 1, choose k minus 1. And we're going to choose Q. Well, we have to choose Q so that it satisfies the inequality, right? So we're going to choose Q. We also have beta here. This is our beta. So let me write. Okay, that's our beta. Essentially, given this beta, oops, we're going to choose Q. Beta is above. And Q, we're going to set it to be 1 over beta natural log of n over r, so that we have this inequality. Times n is n most r. Okay? By choosing this. I believe that's correct. Is that right? Yes, right. Okay. Good. Now, then the conclusion, we choose R beta Q. The conclusion is we can find a collection of containers. There exist a collection of containers for intersecting families, call it Fi on N, where the number of containers where I goes from 1 to, well, we choose its number of containers is at most number of fingerprints. Number of fingerprints is capital N. Capital N is this guy. Oh, I forgot to say what's capital N here. It's a number of vertices in Canesa graph. So capital N choose Q, the size of the fingerprint. Okay. Each of size, this container are not too big. Size means the number of sets, k sets in F is at most capital R plus Q, such that for every intersecting family F, we have I exist I such that F, this intersecting family, is contained in one of our container. This basically follows from using the container theorem we just proved. I will skip the details. It's essentially calculation to verify that you can indeed use that. Okay. And finally, to prove the counting result of the theorem, let me remind you the theorem. This theorem. Yeah. Okay. Now, good. And this is capital N. And remember, in particular, the number of all intersecting families, K uniform, of course, is at most number of fingerprints, which give you upper bound on the number of containers, times the number of how many intersecting families a container can contain, which is 2 to the capital R plus Q. And if you do some calculation, this guy is basically look like 2 to the 1 plus 2 to the 1 times oops. Okay, this implies this. You do the calculation. I will skip the calculation. Any question? So you might ask where exactly in the proof that we cannot get 2K, you have 2K plus 1. This is a natural question to ask. We know it's not true. Because of this complementary pair construction, you get exponentially more. In this proof, it's hidden in the proof. Basically, here, this R, remember R is 1 plus epsilon times n minus 1 choose k minus 1, which is the shape we want. And Q is lower order term. So this requiring n is at least 2k plus 1 is so that this term becomes this error term here. When n equals to 2k, this is not true anymore. This is not error term. All right. Any question? Okay. Very good. If there's no question, we're going to move on to the next application. Now, this is an application of graph container. So let's start talking about hypergraph container. But still in the rather informal sense, because the full statement of the hypergraph container theorem is quite technical. Listing this whole technical theorem, I don't think it's that illuminating. So let's start with an informal explanation and see some concrete baby example of hypergraph container theorem, how we can use it. I think we get more feelings and intuitions about this statement. So let's start with informal informal introduction of hypergraph container. So this hypergraph container is, well, as the name suggests, Kleiman and Winston introduced this graph container. Naturally, one can think, what about hypergraphs? Can we also have some sort of container theorem as long as this hypergraph is locally dense or, I don't know, has some nice property? So hypergraph container. And this turns out to be true, and it was developed about 14 years ago, about 13, 14 years ago, by two group of people, Ballock, Morris, Samoti, and independently Sexton and Thomason. Roughly speaking, at a high level, if we have a hypergraph that where the edges are distributed evenly, uniformly, there's no one part that's too dense, there's no other part that's a patch that's too sparse. This is kind of uneven, right? Somewhere it's too dense, somewhere it's too sparse. Suppose that it's smooth, the edge distribution. So roughly speaking, if a hypergraph has a nice uniform or even edge distribution, then its independent sets exhibit a clustering phenomenon. Clustering phenomenon just means, as in Kleiman-Winston, when you have locally dense condition, this time in terms of locally denseness, we say, okay, the edge distribution and is nice, which is a more vague way of saying it's locally dense, right? If your edges are smoothly, uniformly distributed, like in the random graph, then every patch you should have expected number of edges. Now, clustering just means we can use small fingerprints to group the independent sets together into few groups of containers. That's the clustering we're talking about. Exhibits a clustering phenomenon. What it means is that there exist a few containers such that every independent set is in some of them. Okay. And we also need these containers to be not so large in terms of both the vertices and edges. For otherwise, you just take the whole vertex sets of the hypergraph. That's meaningless. Okay, this is the informal so then you have clustering phenomenon. Okay, informal description. Now, again, let's write down how a hypergraph container theorem looks like informally. Informally, well, we have a uniform hypergraph. Some uniformity K, say uniform hypergraph, where edges are nicely, evenly distributed. Nicely, evenly distributed. Then there exists a family of containers. Let's call it C, such that, well, first of all, we have to justify the name of container. Every independent set I in H, we have a container C in C, such that I is containing this container C. Second of all, this is not anything. This is not a miracle. We can just take script C as a single set, single element consists of these. This is too large. So second of all, we need to say the container is small. So the number of containers is small. We don't want too many containers. Otherwise, for each independent set I, you take a container. That's useless, right? Number of containers C is small. Third of all, you don't want to take the whole set of vertices. Each container also has to be small. So this small is quantified by each container C in C is almost independent. In other words, the number of edges spanned by C is small. Okay. The third one is useful because oftentimes it can be combined with removable lemma to split up the container, saying, okay, the container consists of some junk sets of negligible size plus majority of it is a genuine independent set. Okay, now, for now, I'm not going to state the formal version. This informal version, I think, already sort of illustrate how a hypergraph container theorem looks like. Now let's see a specific example of this through an application. Let's count, as we mentioned last week, the number of triangle-free graphs. This counting problem. So let's recall. Let's see an example through recall. For every extremal problem, we can ask for a counting problem, right? Here's the extremal problem of number of edges. If you have an n-vertex triangle-free graph G, then the number of edges is at most n squared over 4. There's some floor. Okay, let me put 4 here. And the optimal is complete bipartite graph. Now we can also ask for a counting problem. Let me move on to the next page. Okay. Now let's counting problem is what's the number of labeled triangle-free graphs on vertex sets 1 to n vertex. Well, trivially, we have a trivial lower bound is at least 2 to the n squared over 4, just by taking all subgraph of this guy. Okay. Oh, please. This is proved by Erdős. Oh, who proved it? Erdős, Kleiman, and Rothschild that this lower bound is tight, at least in terms of algorithm. Logarithm is asymptotically optimal. So how do I want to say it? In which order? Okay, this way. This is a lower bound, okay? But there are many, yes, yeah, okay, let me write it. So, yeah, okay. So Erdős, Kleitman, and Rothschild prove that this lower bound is, in terms of logarithm, is asymptotically optimal. So the number of triangle-free graphs on n equals to 2 to the 1 plus little o 1 times n squared over 4. Okay. Now when you ask extremal problem, counting problem, there's one step beyond counting problem called typical structure. Let me also briefly mention. So the typical structure what does that mean? Let me explain through an example. Erdős, Kleiman, and Rothschild, they not only prove that the number of triangle-free graphs, the upper bound, 2 to the 1 plus little 1 n squared over 4, they also prove that typically a triangle-free graph is bipartite. So almost all triangle-free graph on n are bipartite. So the typical structure means the structure of almost all graph. So what does this almost all means? This almost all, what it means is that the number of bipartite graphs on n divided by the number of triangle-free graphs on n, when you take the limits, n goes to infinity, this tends to 1. So That means among the universe of all labeled triangle-free graphs, when you uniform random pick one, then with probability tending to 1 as n goes to infinity, this triangle-free graph must be bipartite. This is the typical structure. And certainly, we cannot remove this almost all. There are many, exponentially many when you fix n, triangle-free graphs that are not bipartite. Look, for example, I can take blow up of C5, which has n squared over 5 edges. Then you take all its subgraph, you have 2 to the n squared over 5 that are non-bipartite and triangle-free, right? There are exponentially many that are not bipartite. But this, if you compare this, is a lower order term to this 2 to the n squared over 4, exponentially fewer. So they are negligible. Okay, any question about the statement? All right. So how do we do this? Well, the proof is quite simple. As long as we manage to rephrase counting triangle-free graphs on n as counting independent sets in certain hypergraph. So recall in Ehrlich Colorado, we somehow managed to associate intersecting families to independent sets in Knaser graph. So now we're going to also build some auxiliary hypergraph so that every triangle-free graph somehow corresponds to the independent set in this hypergraph. All right? What will be a natural way to construct such hypergraph? Previously, in the intersecting family, we have every family correspond to an independent set. So this K set must become a vertex in the auxiliary graph, which is the Knaser graph. Here we have the graph correspond to independent sets. So every graph consists of the edges. So naturally, we must use edges, all possible pairs that could be edges, as vertices of our auxiliary graph, hypergraph. So you're going to use all pairs on n as the vertices. But what will be the edge set of the hypergraph so that triangle-free graphs correspond to independent sets? 3 edges form a hypergraph. Sorry. 3 edges, if they form a triangle, they form hyperedges in the hypergraph. So that means if you take independent sets in the hypergraph, this set of vertices correspond to a set of edges in on n must form a triangle-free graph, right? That's how we do it. So phrasing. So as it turns out, we will see many examples later that many problems can be rephrased. Discrete combinatorial problem can rephrase in terms of a problem about independent sets in certain auxiliary hypergraph. Okay, as I said, consider G. So this is the family we cared about, the family of all triangle-free graphs on vertex at n that's labeled. Now we're going to construct a 3-dimensional hypergraph, auxiliary hypergraph. H with vertex set V and E, edge set E, where the vertices are pairs in N. Or you can think of it as the edge sets of Kn, all pairs in N. And for the edges, basically every triangle in Kn give rise to a edge, a 3-edge in H. All right. Any question about? It's hard to draw a picture. I can try to draw a picture when n equals to 4. This is our complete graph. Kn, right? Now the vertices of the hypergraph, the edges of the complete graph becomes vertices. So we have 6 vertices. And 3 vertices form an edge when these 3 vertices correspond to 3 edges from a triangle. There are how many triangles? Whenever you remove a vertex, you get a triangle. So the number of triangles is 4, I believe. 1, 2, 3, 4. So this is a 6 vertex. The corresponding edge has 6 vertices, 6 vertex, 4 edge hypergraph, 3 uniform. Right? So how does it look like? We have you have this is a hyperedge. This is a hyperedge. This is a hyperedge, right? And then there's one more, which is this triangle. So these 3 also form a hyperedge. So how do I draw it? Oops. How do I do it? This is a hyperedge. Is this way slightly better if I draw it? I don't know how to draw it in a nice way. So let me try this way then. It doesn't matter, you know what I mean. Okay. So now, as I said, if you have a set of vertices here in this hypergraph, a set of vertices correspond to a set of edges, subset of edges of the complete graph. If it's an independent set, that means there's no triangle or corresponding set. In other words, through this auxiliary hypergraph, we independent set, so triangle-free graph in G, there's a one-to-one correspondence labeled to independent sets in our auxiliary hypergraph. Good. So in particular, the number of triangle-free graphs, cardinality of discrete G equals to the number of independent sets in H. Now let me finish today's lecture by, now we can make this container theorem rigorous for a specific example for this. We're gonna phrase it for this hypergraph for triangle-free graphs and then we translate back to triangle-free graphs. We're going to create a collection of containers for triangle-free graphs. All right, and remember these three conclusions. One, every triangle-free graphs correspond to an independent set. Every triangle-free graphs must be containing one of these containers. And the number of containers, there are not so many of them. And each container is almost independent, meaning that, remember, the edges in this hypergraph are the triangles. So every container containing these triangle-free graphs are almost triangle-free. So meaning the number of triangles are not so many. If the triangles are not so many, combining by removal lemma, you can remove all triangles by removing few edges. Let's write down theorem. Containers for triangle-free graphs. So for every delta bigger than 0, there exists a C depends only on delta, such that there exists a family of containers, a family of graphs, F. A family of graph is a subset of 2 to the n choose 2, satisfying each triangle-free graph is contained in one of these graph container. So exists the container F in script F such that it contains this triangle-free graph G. Second of all, the number of containers, there are not so many of them. There are number of containers is at most 2 to the C times n to the 3/2 log n. Well, just keep in mind, this is 2 to the little o n squared. Actually, this weaker bound is enough for our purpose, but sometimes this stronger bound is useful for some transference, for some probabilistic results. There are very few of the containers. Why this is few? Well, the total number of graphs, most of the graph, typical graph has this many edges. So the number of graphs, the significant order of magnitude is 2 to the n squared order of magnitude. So here's this 2 to the little o n squared, which is negligible amount. The third of all, each container cannot be too big. I mean, we can simply just take the whole graph, whole complete graph, then trivially it is satisfied. Well, f even equals to 1, right? It's useless. So we want each member in F, they are almost independent. This is the third one. Almost independent means they are almost triangle free. Each F in F is almost triangle free, meaning number of triangles is at most delta n cube. Any question about the statement? So here's the remark that I have earlier. The triangle removal lemma says what? Well, it says that for every n vertex graph, if the number of triangles is at most delta n cube, a negligible amount, triangle density is small enough, then we can remove a negligible amount of edges so that the graph is triangle free. We have that for every container. Here, we have F can be decomposed into a triangle-free graph. And here, this is a graph with little o n square edges. Okay, triangle-free, and which then implies by Mantel's theorem, it cannot be too large. So we actually have a fourth property saying that for each f in F, the number of edges is at most 1 quarter plus little o 1 times n squared, right? You have a Juncker set plus n squared over 4. If you don't know removal lemma, I suggest you to go back to look up my spring course earlier this year. But for now, you can just take it as a black box, saying that, okay, if a graph is almost triangle-free, a little O of n cubed triangles, you can partition its edge set into two parts. Negligible amount, little O of n squared, and the remaining majority is triangle-free, which by Mantel's theorem is most n squared over 4. Okay, now let me finish the Erdős, Kleiman and Rothschild's theorem, at least this part of counting. Now the counting is easy. Essentially, by this container theorem, the number of triangle-free graphs, right? So the number, triangle-free graphs on n is at most, well, this is at most, we know each triangle-free graphs is, by the first property, is containing one of the container. So it's at most, we multiply by the total number of containers, and each container is not too large, right? Times 2 to the 1 and 4, 2 to the n squared over 4 plus little o n squared. Then this, by the second property, is 2 to the little o n squared, 2 to the n squared over 4 plus little o n squared. We are done. Any question? Once again, every triangle-free graph is containing one of these containers. So you sum over all containers, number of containers. Each container contains at most 2 to the e of f, meaning subgraph. So we know e of f is at most n squared over 4. Okay. Any question? All right, if there's no question, I'll see you guys on Thursday.